Right, this is the video key for exam 2 from 2015, exam 2 for 2015, unit 2. Right, so the first question here is looking for what happens in a Uv-Vis experiment. What is detected? So an electron in a pi bond absorbs the Uv-Vis, ultraviolet or visible radiation, and is excited into a pi star antibody orbitals. Bonds aren't broken, but an electron gets excited from pi to pi star, and it tells us about conjugated pi systems with either lone pairs or pi bonds. Lone pairs or pi bonds. So this next one's a mass spec question. What two structures form from the major fragmentation for the molecule below? So here's the molecule. It's very symmetrical. And for major fragments, we'd want to have the most stable fragments, which would probably be tertiary carbocations, right? Carbocations are stabilized by hyperconjugation. That's one of the ways. And so the most common way, the stable fragment would be one of the ways to form a tertiary carbocation, which is by breaking this bond or this or this. The molecule is actually very symmetrical as well. Now that same idea, the least likely fragment would be one that forms a primary carbocation. So either here, or here, or here, or here, or form a primary carbocation. That'd be the least likely. Right? Primary carbocation and a methyl radical. And the part that's actually detected are both always the positive fragments. It's never the neutral radical, it's always the positive fragment piece that is actually detected. So over here again, would be the positive fragment. The second part here is a question that asks how many peaks would you expect in C13 for this molecule. Now again, this molecule is very symmetrical, so essentially these pieces are all the same. So you'd guess 1, 2, 3, 4, and then 5 for the middle one. That's how many peaks we expect in the carbon NMR. So this next one, number 3, we're showing a gamma cleavage and a heterolytic cleavage. Now gamma cleavage is maybe something you didn't know, but that's okay because if you look at what's going on here, you should be able to figure it out anyways. So the first thing is we want to show the molecular ions. So we want to draw the product twice. So one electron is getting kicked out. Draw electron twice. Down here it says heterolytic cleavage. Show arrows in both products. So heterolytic cleavage, both electrons go to the chlorine. So the heterolytic cleavage. So you need a chlorine radical, neutral chlorine radical, and then a secondary carbocation in this case. Now a gamma cleavage is maybe something you haven't seen, but that's okay because you're given the actual product. So you can look at it and say, you should probably number these carbons. Maybe this H1, 2, 3, and 4. Right? So this is carbon 4. That H is 1, it's there, and here is 2 and 3. So kind of looking at what bonds need to be broken, what bonds need to be formed. It's a pretty challenging question, but you should be able to figure it out. So essentially this CH bond is what breaks. And that chlorine now is bonded. There's a chlorine H bond, right? There's a new pi bond formed between 3 and 2. And the bond between 3 and 4 is also broken. Right? Again, homolytic cleavage, moving one electron at a time. But pretty challenging question. Number 4 here is more of a theory kind of question. If the molecule below was used only a heterolytic cleavage form, why will this not undergo alpha cleavage or homolytic cleavage? That's because the bromine is so much larger that the bromine will not want to form a pi bond that has an alpha cleavage. Also, the carbon-bromine bond is weak because there's less orbital overlap because the bromine is so big. So this is the one that's going to most likely break in a heterolytic fashion when the two electrons are going to go right to the bromine. Whereas in chlorine, you can have both heterolytic and homolytic cleavages, like an alpha cleavage. Here's a question about theory about IR. So a ketone stretches at 1715 in IR spectrum. Predict whether the CO stretch with the other carbonyl, which is an amide, would be lower or higher. Explain your reasoning. So again, looking at this to say nitrogen, well, nitrogens you should recognize what would be willing to do resonance. So the resonance structure, the two electrons go there to form a new pi bond. The pi bond breaks, electrons go to the oxygen. Because of that, this cetyl bond O is going to have some single bond character. It has some single bond character is going to stretch at a much lower frequency because it's a longer bond, right? So single bond character from the resonance. So we expect it to be lower. This next one is which compound matches the IR spectrum below. Label important peaks and describe how you determine this. So I would go through this, maybe look for. So these first two have OHs, right? A carboxylic acid OH and a regular alcohol OH. And if you look here, there's no real big OH in this region. So you can usually eliminate these two. Now after that, you probably notice these two CH stretches at 2820 and 2720. That's your classic aldehyde CH stretch. Right? So we think there's an aldehyde for sure. Right? Now, the distinguishing between these two, this one has a nitrile, which we know stretches about 2200. I don't see anything at 2200, so by process elimination, it's kind of stuck with this one. You can even see there's two different types of carbonyls as well. So maybe that the two carbonyls are shown there. But again, process elimination, no OHs, so that immediately eliminates these two, and no nitrile. So really the only answer is this third one. For number 7 here, it's about picking out the number of non-equivalent hydrogens or protons, and then also think about what the splitting pattern would be with these. So this is a molecule here. We'd have 1, 2, 3, 4 types of hydrogens. So starting with A, this A has one nearest neighbor, so we predict that would be a doublet. B can hear A, but it can also hear C, so it's going to be a complex splitting. So it has two hearing two songs. So B is going to be turned into a quartet by A, and it's going to be turned into a triplet by C. So a triplet of quartets or a quartet of triplets. C, again, is also hearing two different songs. It hears B and it hears D 3 bonds away. B is turning C into a doublet. And D is also turning C into a doublet. So it would be a doublet of doublets. Finally, D. How many nearest neighbors does D have? D only has one nearest neighbor, so D itself is also a doublet. The trick here is, again, this highly symmetrical type molecule. That's why D is a doublet, and also why they're turning each other into a doublet. So be careful with that high symmetry of the molecule. So the next one, a lot more complicated, but again, highly symmetrical. Again here, highly symmetrical. So either way, this molecule originally, you can't quite see it anymore, was this. Right, so lots and lots of symmetry. So one type, 2, 3, 4 types. There's only 4 types here. So A, those would be singlets. There's no nearest neighbors there, but worth 6 hydrogens. D here would have 4 nearest neighbors. So 4 plus 1 is 5, so it would be a pentet or quintet, you could say. B is in the out here. B, all these B's, which would be 3, 6, 9, 12, have 2 nearest neighbors, so that'd be a triplet. Be highly symmetrical. Then C would hear D, which turns into a doublet, but it also would hear B, the 3 there, which would turn into a quartet. So again, highly symmetrical. You gotta be careful with those highly symmetrical molecules. Here's a nice question about how you explain how you use a method of characterization we talked about in class to differentiate between compounds. Right, you can name the technique and explain the information it would give you, but you can only use each technique once. Right, so you're using your Uv-Vis, your mass spec, your IR, your Proton Nmr, and your carbon NMR. So this one I think would be easiest to use. You could use mass spec because of the different fragmentation, the branching, or you could use Proton Nmr. There'd be a different number of H's, types of H's. The integration and splitting would also be different. For this one, again, I think you could use IR. Right, IR will tell you OH versus carbonyl. Right, that'd be there. Mass spec would give you a different fragmentation pattern. It'd be the same mass, a different fragmentation pattern. Or again, Proton Nmr again would easily differentiate based on the different numbers of H's and the splitting and all those good things. For C, again, you have a trans and a cis molecule. So again, IR would tell you that different CH bends, right? Those in the fingerprint region, or NMR would give you the 2 different coupling constants. But again, here the trick was you can only use each technique once. So make sure you be careful not to double down and do that, and then to do a good job explaining what's going on. Notice the explanations are worth 3 points. The technique was only worth 1. Now, I guess this is one of these challenge problems. So show your work in a certain structure from the data below. So we have a mass spec of 140. So that should make you think of the nitrogen rule. So it had an even number of nitrogens. You write that there. The IR, you see a peak at broad and strong at 3450. That should make you think of OH or maybe an NH, but I'm just going to go with OH. 3300 in sharp, that should tell you SP CH stretch, a terminal alkyne. Stretch at 2975, that should be SP3CH. And 2195, I'm thinking that's a CC triple bond because I also saw this SPCH, so I think it's a CC triple bond, right, because of the one at 3300. So at this point, we turn our attention to the NMR signals we give. So at 4.52, I'm labeling these, of course, A, B, C, D, E, and F. Give these all labels. At 4.52, I see a 1H. That's a broad singlet and disappears to D2O shake. That tells me it's an OH. So oxygen and hydrogen, so that's an OH. That's one of my pieces I've circled. That HA is there, and I'm going to subtract that total from the amount of that. So it's 17, oxygen plus hydrogen 17. So I subtract that out. The next peak I'm going to look at, I kind of go to the other end of the spectrum maybe, from the most D-shielded to the most shielded. 0.84, I see 9 H's, that's a singlet. That makes me think of 3 CH3s on 1 carbon, so a piece like this, because they'd all have to be the same, right? All have to be the same, and they're a singlet, so I see 9 of them, I think that's 3 CH3s on 1 carbon, so I could subtract that piece out, so that weight would be, I believe 57, 12, 48, plus 9, 57, right, so that's for F. So as I say, I didn't subtract it out here until the end. I actually did the alkyne piece first, which is another one you could look at. Right, the 2.93, 1H is a singlet. That's an alkyne stretch. So that's that one other piece here. It's on the other side of the alkyne. So it's a singlet, so it has no nearest neighbors as well. So it's 2 carbons, 24 plus an H is 25. That's for that alkyne. Got 98. Now I subtract out my F, the 57. So now I'm down to 41. So what do I have left to do? So I've checked off, let's see, I've checked off the D2O shake, the OH, I've checked off the terminal alkyne, I've also checked off the 3 CH3s. I have left is these 3 more peaks, and they all appear to be kind of coupled to each other, and it looks like E is coupled to both D and B by knowing that they're coupling constants. So 2 different coupling constants, basically E is hearing 2 songs. So E is 1H, so I think it's a C with an H, HE. And on either side of HE are B and D, right? B and D, because E is a triplet of triplets, so it'd have to have 2 CH2s on either side of it. I know that's coupled to both D and B. This whole piece adds up to 41, so we'll go count that out. So now we have our pieces. We have 1, 2, 3, and 4. Now we got to start putting these together, and we want to go back, right? So check off. We want to go back and look at the frequencies now. So this is the OH, so that's kind of going wherever. But this one at 3.54, that should tell you is probably near an oxygen. Probably near that oxygen, that's HB. So let's put HB near that OH, right? Near that OH. D, HD, let's put near on the side, the alkyne side, right? And then put the CH3, right, off the HE, right? So that way they'll all be the same. Now, one alternative, people would probably say, well, how did you know the alkyne piece was on that carbon versus why didn't you switch these 2 around? HD is actually it's a little more D-shielded, so you'd guess it'd be closer to that pi bond, kind of an allylic position, so I want to put the alkyne closer to HE because of the allylic position. Again, though, find your pieces, right? Find your 4 pieces and start putting them together based on the actual frequencies. All right, going again to number 10 here. The other one is show your work and determine the structure from the data below. Given the molecular formula now, due to degrees of saturation, it's 6, so you immediately think ding, 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 benzene ring. It means you have 2 left. Go to your IR, 3033. That should tell you sp2 CHs. 2980, sp3, 1692. That makes me think, right? That makes me think carbonyl, right? And I'm saying not all the peaks are given, so maybe we're missing the aromatic stretches. If we're not sure about the benzene ring, looks like we do have protons in the benzene ring because we have peaks at 7.99, 7.46, right? That gives me an indication that it's an aromatic ring. The substitution is going to be a little different because there's only 3 aromatic rings, or aromatic protons. That means the ring is going to be substituted 3 times. The other thing I should notice here is that it's C13H16O2, but I only have 1, 2, 3, 4, 5 peaks. Very symmetrical molecule, most likely. Very symmetrical. Few peaks, very symmetrical. And maybe even thinking 2 carbonyls to get those last 2 degrees on saturation done. So maybe 2 carbonyls and very symmetrical. So right now at this point, we've done the IR, we've covered our degrees on saturation, we've written down, right, this must be symmetrical, there's very few things going on. Let's look at our proton NMR. So labeled A, B, C, D, and E, so we have 5 types. it looks like, according to the coupling constants, A and B here, the same coupling constant, they must be coupled to each other. One's a doublet, one's a triplet, and they're on the benzene ring. So how we substitute the benzene ring must be like this. We have three things, because we only have three aromatic H's, and A needs to be the same. That means these two things here, the starred portions, must also be the same to make A the same. So A would have one nearest neighbor, so A would be a doublet. B would have two nearest neighbors, so B would actually be a triplet, so that matches up. So this is the one piece, the first piece. If we go to C, we see at C here, C and E are coupled. Notice the 7 Hertz coupling constant. 1H is a sextet, which means it would have to have 6 nearest neighbors. Or sorry, actually a septet. I'd have 6 nearest neighbors. Actually, should be a septet there. Excuse me, that's wrong. It should be a septet, right? It has 6 nearest neighbors, n plus 1, so it should be 7, right? And that looks like it's getting coupled to, right, two CH3s, right, the same ones. That'd be a doublet, right? So that would be this piece right here. Excuse me, I got back up a second. I didn't subtract out our first piece, C6H3 from our molecular formula. So we have C7H13O2. If we take out C3H7, which would be C and E, the two pieces are coupled, the septet, not sextet, the septet. We have left with C4H6O2. Very good. And now you have at 2.5, 6 H's that are singlets. That's that right now, allylic region. That should be maybe those carbonyls at this point. So 2 carbonyl pieces. So we'd have 2 carbonyl pieces for HD. The singlets and no nearest neighbors. So now we have 1, 2, 3 pieces, and then 4 with our ring. And our ring has 3 spots. We got to put the 3 carbon piece in the middle, and 2 carbonyls on the side to get the correct answer. Again, septet, not sextet.